This is Giancoli problem 2115. Now Giancoli says that this is a level 2 problem. I think it's borderline 2-3. These are one of those problems where I just kind of laugh when you get to the answer, because you look at it and you think there's no way that these things are even related. But here we go. So the idea is you're pulling this coil out of a magnetic field, and the coil hates to have a change in flux. And you can actually feel that hatred, or the screaming, don't change my flux, by needing to exert a force on the coil to keep it going. If you let it go, it would slow down until it stopped, actually. I'm not sure with these dimensions that it would. So just picture with me, as you pull the coil over with this speed, you're changing the flux through it, because this edge comes out of the, more and more of the loop is coming out of this edge where the magnetic field stops. So you have to think about where the energy that you're putting in goes, because a force times a distance is energy that you're putting into this system. Its potential energy isn't changing, so where's that energy going? It's being dissipated in the resistance of the wire. You're actually heating up the wire, pulling it out of the magnetic field. It's kind of crazy. The book didn't draw it like this, but I like to just tell myself, oh yeah, this wire has some resistance. And so I wrote it right here. So let's write this, what I just said, in an equation. I said that the force times the distance divided by the time, okay, change in d over time. This is how much power I have to supply to get it out. Force times distance is the energy. You just divide by time and you get the power. Now, let me just show you something here, though. This stuff that I'm dotting in blue, we know and love as the speed, okay? And that's a weird V. You'll see why, because I'm going to use capital V in just a minute. But that's the speed of the loop. So that tells me how much power I'm exerting by, or supplying by exerting this force. We can set that equal to another way to calculate the power here, and this is the power dissipated in the resistor. And so I'm going to call that V squared over R. Now typically I'd write down IV. I'm looking ahead here. I don't want to, I don't want to have to find the current, because the current is equal to 1 over R times V. So I'm just making this substitution to begin with, and I'm left with V squared over R. Well, I can divide by this dotted blue thing to solve for the force. I know I want to do that because that's what it asked for, was what force do you have to supply or apply to keep this moving at this constant speed. So I know that force is the voltage squared divided by R times little v, the speed. Oh boy, now we have to look at the voltage. The voltage exists here not because there's any battery, but because as you pull it out of this magnetic field, it screams. This is the screaming. And so we come back to Lenz's law, the Lenz-Faraday law, and V is equal to the number of coils. It's just one wire here, so I don't have to write N, or N equals 1. That's how you would say that, times the change in flux, magnetic flux, over the change in time. Oh dear. Now we've got to find out how many field lines leave the loop as this goes. Well, hopefully there's something up ahead that helps us find that. Let's just write down what the change in flux is. I mean, it equals the magnetic field times, let's call it the change in area, because really it's not the area of the loop that matters. It's the change in area as time goes by, meaning the change in the area that's in the magnetic field. Because if I move this way, parallel to this boundary between magnetic field and no magnetic field, then the magnetic field never changes. There'd be no voltage, and you would have, it requires no force to keep it moving at a constant speed. It's only because as this leaves the magnetic field, it screams. That's why you have to supply energy to keep it moving. Okay, well, that's my change in flux. It's not really helpful in that form, though, because I am still, this just blows my mind trying to think about how the magnetic field, the amount of area is changing as time goes by. See if you agree with this, though. The width is always the same, so I'm going to write W here. And then the width, what changes is the change in, say, X. It's this dimension, right? The X part, the length part of it, changes in time. This is just a constant. Now this, oh my word, looks just like velocity. And it's not a coincidence. It is the velocity. And so it's the magnetic field times the width. You know, the wider this is, the more change we would have. But it's constant. I mean, once you've set that, then you multiply by the speed and you win. This is the answer for the voltage part. It's equal to B times the width of the coil times the speed of the coil. Okay, that is just nasty thinking, but you have to think, I mean, the key here is to think about what's constant. What is changing the magnetic flux? The magnetic field isn't changing. The area is changing. And then in the area, which is width times the X, call X the part that's inside here. Oh dear, there's so many X's. You know that those just mean into the page, though. This is the special X that is the area. The area of the loop that's in the magnetic field is the width times this X variable that I've made up. It's not L. The length of it is all of this, but not the whole length is in the magnetic field. So now, once you've got area written this way, you can see W doesn't change. The width doesn't change. It's just the X that changes. And it changes in a known way. This is change in X over change in T is equal to the speed. Alrighty, well, we've written down V. Now we've got to write it in our equation. So V squared is B times W times V, all of that squared over R times V. So the force is equal to B squared, W squared, V squared over R V. Those cancel. And now I've just got to plug it in. Hold on, I'm going to write it on a new sheet. All right, now I'm just going to enter the numbers here for each of these things. All right, there you go. You can see that I have put them all in scientific notation. First thing to do is take care of these squares, which I'll do right now. So 5.5 squared, well, 5 squared is 25, 6 squared is 36. I don't know, what should we call it? let's just call it 30. And now I got to square the 10 to minus 1 times 10 to minus 2. You just multiply the exponents. Tesla squared. I'm going to drop units here in a minute because this is getting ridiculous. 3 squared is 9, 4 squared 16, so 3.5 squared, I don't know, maybe 12. Again, times 10 to the minus 2, multiply those exponents. All right, and now 3.4 just carries through. And we divide by 2.3 times 10 to minus 1. Joules per Coulomb amps. Good luck with those units. I mean, I'm just going to assume they work out. I made sure on the other page that my equations, I kept everything, you know, magnetic field times a length divided by time. That is a voltage. I know that. And then I plugged it in here. A voltage squared divided by an R times a velocity is going to be equal to a Newton. So good luck. If you want to show me, that would be nice, but I'm not going to expect it. Okay, 30 times 12 is about 360. So we have 360. And we got these two that are about 3/2, so that's 1.5. Oops. Okay, we've taken care of all the numbers, and now we just need to multiply times 10 to the 10 to minus 2, subtract 2 is minus 4, and then we divide by 10 to minus 1, so we're at minus 3. All right, 1 1/2, half of 360 is 180, so you add 1 plus a half is equal to 540. So we have 540 times 10 to minus 3, so that equals 0.54 newtons. This was always in newtons. Obviously, Tesla squared, meters cubed, Coulomb amp per joule second is a Newton. You can file that away for later on in your life. I'm sure it'll come in handy.